Have you ever just stopped and wondered what you would see if you could travel at the speed of light? It sounds like sci-fi, but it's one of the most important questions in all of physics, and it's the exact question a young Albert Einstein asked himself. So today, we're going to follow his train of thought, step by step, to see how that one simple question completely blew up our understanding of space and time.
You know, it all starts with one of Einstein's famous thought experiments. He pictured himself just riding alongside a beam of light. And at first glance, that seems totally fine, right? I mean, a duck can swim as fast as a water wave. It can just tattle along and see the wave crest stay right next to it, completely still. So why on earth would a light wave be any different?
Exactly. Think about a fighter jet pilot hitting the speed of sound. They're basically outrunning their own engine noise. The sound waves are, from their perspective, just frozen relative to them. And that's fine. No laws of physics are broken. But doing the same thing with light? Well, that creates a huge paradox, one that threatened to bring the whole structure of physics crashing down. So what is it? What makes light so special?
To really get to the bottom of this, we have to rewind the clock a bit, back to a principle that was set in stone long before Einstein ever came along. It's a fundamental rule about how motion itself works, and it's called Newtonian relativity.
Okay, so the core idea here is actually pretty simple. Imagine you're on a super smooth train and all the windows are blacked out. As long as that train is moving at a perfectly constant speed, no bumps, no acceleration, there is no experiment you can do inside that car to prove you're moving. If you toss a ball, it'll act normally. A pendulum will swing just like it should. As far as you're concerned, you might as well be standing perfectly still.
So let's try to break this rule. Imagine Einstein's in his car, moving at a steady speed, and he just tosses a ball straight up. You'd think the car would move out from under it, right? But it doesn't. The ball lands right back in his hand. Why? Because of inertia. The ball already had the car's forward speed when he threw it, so it just keeps moving forward with the car as it goes up and down. The experiment fails. It tells him nothing about his motion.
Okay, fine. What about a different test? He takes a toy gun. Same deal. The little bullet inside already has the car's forward motion because of inertia. So when he fires it, the gun just adds its own speed on top of that. The bullet zips forward perfectly normally. Again, the result is exactly what would happen if you were standing still. So, another failure.
So here's the big takeaway. You can't use particles, balls, bullets, anything with mass to detect your own constant motion. Inertia is always there, making sure the experiment looks exactly the same whether you're moving or not. It's like this rule is just ironclad.
But then Einstein realizes, wait a minute, there might be a loophole here. Everything we've tried so far involves particles, and particles have inertia. But what about waves? Waves behave in a totally different way. Maybe, just maybe, they're the key to finally detecting absolute motion.
And this is where it gets really, really interesting. Look, the speed of a bullet totally depends on the speed of the gun firing it, right? But a wave is different. The speed of a sound wave only depends on the medium it's traveling through, like air, not on how fast the person shouting is moving. And that is a huge deal.
This feels like the breakthrough. If Einstein gets his car up to the speed of sound and then shouts, the sound wave he creates will move forward through the air at its normal fixed speed. But since he's already moving at that exact same speed, the wave should just hang there, right in front of him, totally frozen. And that is something that would never happen if he were at rest. It looks like he's done it. He's found a way to detect his own motion.
But not so fast. Einstein comes up with this brilliant little excuse. He could just say, whoa, I'm not moving. My car is perfectly still. What's actually happening is that the air itself, the medium, is rushing past me like a giant wind. The sound wave is trying to go forward, but this headwind is holding it in place. It's kind of like trying to walk down an upward moving escalator at the exact same speed. You just stay put.
You see, this escalator effect is a perfect excuse for any wave that needs a medium, whether it's sound in air or ripples in water. You can always just blame the medium's motion. But there's one very, very special wave out there for which this excuse just doesn't work.
And that special wave, of course, is light. By the late 1800s, thanks to the genius of James Clerk Maxwell, physicists figured out that light is an electromagnetic wave. And the most incredible thing about it? It doesn't need a medium. It can travel through the pure, empty vacuum of space.
And this is the moment the whole crisis comes to a head. If light has no medium, there's no wind, there's no escalator effect, there is no excuse. If Einstein gets his car up to the speed of light and flicks on a flashlight, he would see that light wave frozen right next to him. And that means he could prove he was moving. And just like that, the principle of Newtonian relativity, a cornerstone of physics for centuries, looks like it's about to shatter.
This created a massive standoff in the world of physics. On one side, you have Newtonian relativity, which basically screams that constant motion must be undetectable. On the other side, you have Maxwell's equations for electricity and magnetism, which say that the speed of light is a specific, universal constant. These two pillars of physics were in a head-to-head battle. One of them had to be wrong.
Faced with this impossible choice, most physicists at the time were trying to find problems with Maxwell's equations. They just couldn't believe that relativity was wrong. But Einstein, he took a completely different path. He proposed a solution that was so bold, so breathtaking, that it saved both theories.
He basically declared that the only way to save the principle of relativity, to make sure motion is always undetectable, is to make a radical new rule. He said, what if the speed of light in a vacuum isn't just a constant? What if it's the exact same for every single person who measures it, no matter how fast they're moving?
Okay, but hold on. How can that possibly be true? Think about it. If you're on a spaceship going at 90% the speed of light and you turn on your headlights, your brain tells you that light should only be moving 10% faster than you are. But Einstein is saying, no, you'd still measure that light beam racing away from you at 100% the speed of light. How on earth is that possible? The answer, believe it or not, is hidden inside this incredibly simple equation. Speed equals distance divided by time. It's something we all learn in middle school. But for Einstein's new rule to work, the math of this equation has to be true for every single person in the universe, no matter how they're moving. Now just follow the logic here, because it is absolutely inescapable. If the speed of light is locked in, it's always the same for everyone. But a person moving and a person standing still will clearly measure a different distance that a beam of light travels. Then, for that equation to balance out, something else has to give. The only variable left to change is time itself. And this leads to the first, absolutely earth-shattering consequence of his idea. To keep the speed of light constant for everyone, time itself has to slow down for a moving observer, relative to someone who's standing still. And this isn't some trick of perception. Their clocks, their biology, the very flow of time itself literally slows down. And you know what? By that very same unstoppable logic, space itself must also be flexible. To keep that speed of light constant, the length of an object in its direction of motion has to actually shrink, at least from the perspective of somebody watching it fly by.
So here's the ultimate irony, the big takeaway. To save the idea that all motion is relative, Einstein had to get rid of something we all thought was absolute, the idea that space and time are fixed and the same for everyone. The theory is called relativity, but it's really all about the one thing in the entire universe that isn't relative, the absolute, unwavering, constant speed of light.
And this leaves us with a really fascinating final thought. Einstein showed us that even things as fundamental as time and space aren't what they seem. So it really makes you wonder, right? What other absolute truths that we take for granted every single day are just waiting for the right question to come along and reveal that they are, in fact, relative to?